Hello again, math analyzers. Welcome to Chapter 8, Lesson 3 notes. We're going to talk about sine, cosine, and tangent ratios. Trig ratios. We love it. We're finally there. So this applies to our right triangles that we've been discussing so far. It turns out that there is a relationship between the specific function I can do to an angle and two of the sides in a right triangle. That angle just has to not be the right angle. So we have to figure out which of the two angles are in question, and then we know in that right triangle which side is the hypotenuse, of course, across from the right angle, but then which side is opposite of the angle in question and which side is adjacent to the angle in question. So we need to know what opposite and adjacent mean. Opposite means across from, adjacent means next to. So when I do this labeling, you'll see me kind of use that or say those terms, but just to make sure we know what opposite and adjacent really reference, right? We know the hypotenuse side, it's the longest side, and it's across from the right angle. It's easy enough. Okay, here's where theta starts to come into our lives. Theta, alpha, beta, all that good stuff. We have a tendency to use Greek letters to denote angles that we don't know the measure of. So in trig, a lot of what we're talking about refers to angle measure. So we use theta a lot, which is this guy. Okay. Alpha is also a fairly frequently used Greek letter, as well as beta. Ooh, that was an icky beta. Sorry, that's a better beta. More alliteration. You guys know I love it. We, of course, use SOHCAHTOA to remind ourselves of sine of our angle is equal to the opposite over the hypotenuse ratio. The cosine of our angle is equal to the adjacent over our hypotenuse ratio. And the tangent of our angle is equal to the opposite over the adjacent ratio. Now, I say ratio because, yeah, these are fractions. And that's the relationship of the sides to this function of the angle that we can perform. Okay, sine, cosine, and tangent are functions that we perform to the angle measure to get a specific value, and that value matches the value of opposite over hypotenuse or adjacent over hypotenuse or opposite over adjacent as far as the values of the sines divided. So those two sides equal, right? And they have a tendency to equal non-repeating, non-terminating decimals. All right, we usually, when we're talking about these values, we usually round to the 10,000ths place. So 4 decimal measures is the classic way to reference how these angles are working, okay? Now that we use graphing calculators instead of trig tables that we used to use, we know more decimal values of these, but still something to take note of, okay? Another thing to take note of, notice, even though I see abbreviations on my paper, and those are, I'm sure, familiar to you, I still use the words sine, cosine, and tangent. Okay? Yes, I recognize that sine is abbreviated S-I-N. We do not say sin. Cosine is abbreviated C-O-S. We do not say cos. And tangent is abbreviated T-A-N. Most appropriate to say tan out of all of these, but no, still the tangent ratio. Okay, so please don't say sin, cos, or tan in front of me. It's sine, cosine, and tangent, but yes, those are the abbreviations. Just like axis of symmetry, you always say that, but I write AOS out. I don't know why sine had to be abbreviated to just drop the last letter, but whatever. Right? I didn't make the things up, but these are the classic ways. These are the ways. Theta, alpha, beta. That's a much better beta too. Why is my first beta stinky? Greek letters. That has a tendency to replace our angle measures. Sometimes we use X, Y, Z, but not often. So, should I ask you for the ratios based on an angle that I don't know the value of? Here's how you do it. Here is my angle in question. The first thing I label based on where my angle in question is always the hypotenuse. because that will never change. The hypotenuse is always going to be the side across from the right angle. Notice I abbreviate HYP, but I still say hypotenuse. Same deal. Okay. Now, this is where knowing what opposite and adjacent mean really comes into play. The opposite side from your angle is across from it, all the way across. And the adjacent side to your angle is the one right next to it. So this is the relationship of how we describe the names of the sides compared to the angle in question. So what would be the ratio of sine of theta compared to the specific values that I have in this right triangle? Well, sine is opposite over hypotenuse. So the sine of this theta is 3 divided by 5. Cosine of theta is adjacent over hypotenuse. So the cosine of this angle theta is 4 over 5. The tangent ratio is opposite over adjacent. So opposite over adjacent would be 3 over 4. The tangent ratio is the only one that can be greater than 1. This is the only one that could be greater than 1. These two always have to be less than 1 because the hypotenuse always has to be the longest length. So that would mean this denominator will always be bigger than the numerator, meaning these values are always smaller than 1, between 0 and 1. This value has the opportunity to be greater than 1 depending on where your angle is. Okay, but it won't happen that often. Okay, but just kind of stating, these guys must be less than 1. I swear I do not abbreviate the word B as just writing a B. That was just me being tired. So, how does this compare in a situation where I know my angle measures, right? Down here, right? Looking at these values that we kind of already knew, right? Okay, well, if I'm looking at the 30-degree angle, so this is my angle in question, then this is my opposite side, and this is my adjacent side. And of course, the longest side is the hypotenuse side, so side across from the right angle. Let's do the comparison. Sine is opposite over hypotenuse, 1 over 2. Cosine is adjacent over hypotenuse, radical 3 over 2. Tangent is opposite over adjacent. Oh. Can I leave that? No. I have to multiply top and bottom by radical 3. I end up getting I know this. I know what I did. Again, I'm tired and it's showing. Radical 3 over 3. Okay, multiply top and bottom by radical 3. Now, do it with the same triangle from the 60-degree angle. So this is the angle in question. The hypotenuse doesn't change. But now this is the opposite side, and this is the adjacent side. So now I'm thinking in terms of red. So ignore the blue, think in terms of red for the 60-degree angle. Sine from 60 is radical 3 over 2. Opposite over hypotenuse. 2 is the hypotenuse thing. Cosine of 60 is the adjacent over the hypotenuse. So that's 1 over 2. Oh, interesting. I'm going to point that out in a second. But the tangent of 60 is the opposite over the adjacent. Oh, it's just equal to radical 3. Look at that. Those are all very interesting. And what's really interesting is like these, the sine of 60 and the cosine of 30 are the same, and the sine of 30 and the cosine of 60 are the same. So see why that angle in question matters? That angle in question matters to figure out those ratios. But again, because we are in the same triangle, we are going to have that happen. Okay? So keep those relationships in mind in case you're ever asked about which relationships are equal to each other, right? Opposite angles with the sine and cosine. That's what's going to be equal. Anyway, got to do it with the 45, 45, 90 because you can't leave her out. At least this time I only have to do it once, right? Because even though these are two different angles that are my angle in question, it's still going to be the exact same thing because we're looking at an isosceles triangle. So here's opposite, here's adjacent, and here's hypotenuse. So the sine of 45 is opposite over hypotenuse. Well, crap, gonna have to rationalize that guy. So multiply top and bottom by radical 2, you get radical 2 over 2. And, well, if this guy was an oh crap moment, then this guy's an oh crap moment. The sine of 45 and the cosine of 45 are going to be the only sine and cosine ratios that are equal to each other because they are the same value of the lengths of the sides. So that's the one spot that this is going to happen. And so we can just write radical 2 over 2 because we already did the math. Now, tangent is going to be opposite over adjacent. It's 1 over 1. Yay! So the tangent of 45 is 1. Got our first integer. Cool. Okay, that's where that's going to come into play. All of this matters in chapter 9, big time. Okay, all of that matters in chapter 9, big time. I'll go over it again, but it's good to have in our notes that we've already looked at. All right, it says TI 83, but of course we know we've moved on to TI 84s in most of us. I'll talk about the specials in a second, but let's just talk about general, okay? You do need to make sure that your calculator is in degree mode in order for this to work. So, press mode, and see how I'm in radian mode right now? No good for trig. So go down here and then arrow right. So I'm on degree, press enter. Now the degree is highlighted, and now I'm good to go for using my trig ratios on my graphing calculator. But make sure you've got degree mode. Good Lord, you're going to get this wrong if you don't check for degree mode. And I know it sucks, but your graphing calculator, when it gets reset, goes back to radian mode. So you're going to have to make sure you check for degree mode frequently. Trust me, I've gotten things wrong that way, and it's just a stupid reason to get things wrong, especially for how many times I've said to make sure your graphing calculator is in degree mode. How many more times I'll say, make sure your graphing calculator is in degree mode. So make sure your graphing calculator is in degree mode. Anyway, sine of 21, press sine, and then type in 21, and you get the ratio. I didn't even put the end parenthesis on because I'm getting lazy. I really shouldn't get lazy. But yeah, round to the 4 decimal places. So this would be the 10,000ths. These are the decimal equivalencies. Back when, and I'm not kidding, I did go to high school having a TI-83 graphing calculator. But even I used actual trig ratio charts. That used to be the way to go. Okay, so someone had sat and figured out all these decimal things, right? And just made charts of these. And you used to have to look up the angle measure with the chart. You're so lucky you have graphing calculators, I'm telling you. Took forever for those books to not have the charts in them anymore. Anyway, 4 decimal places, so 0.3584. Okay, let's try cosine of 21 just to prove to you that these are not equal to each other because they are not the same ratio of the sides and the lengths of the angles. They're also not going to add up to 1 if you look at them, right? So the cosine of 21 is 0.9336. Okay, and that just means that the adjacent side divided by the hypotenuse side is going to give me this value. Cosine of 63, okay. Okay, 0.453, 0.45, because I got to round the 9 up, so that rounds the 3 up to 40. And yes, I'll write that 0 in because I'm going 10 thousandths. Tangent of 63, interesting. I was going to say that's going to be over 1 because tangent of 45 is 1. So now we're above 1. 1.9626. Hey, the first one I haven't had to round that last digit. Tangent of 46. Oh, I just mentioned that the tangent of 45 is 1. So we're going to see here that the tangent of 46 is going to be a value greater than 1 because the tangent of 45 is exactly equal to 1. Five. Got it. And the sine of 46, not going to be greater than 1 because sine and cosine are never going to be greater than 1. Okay, so 0.71393, excuse me, 0.7193. There we go. Okay. Special right triangles, we just did all the radical exact values, which are the ones you're going to need, but it's going to pay to be able to recognize, I didn't say memorize, recognize their decimal equivalents. So one thing we've already seen is that sine of 30 is 1/2. And we saw that on the front here when we did this exchange. So sine of 30 is 1/2 or 0.5. Now, what you also will know then is the cosine of 60 will be 0.5. And let me just prove that by doing it right here, just so we can get that out of the way. Okay. Now, the cosine of 30 is going to be the decimal equivalent of radical 3 over 2. And I'll just prove both of those things. Cosine of 30 is this. Now I'm going to take radical 3. Forgot I'm on an 84. See, I had an 83 for so long when I was in high school doing this that sometimes I revert back to my 83 ways. There we go. So radical 3 over 2. You'll want to be able to recognize 0.866 because you're going to see that very frequently on here. Just note that that is radical 3 over 2. So 0.866, and that also means that the sine of 60 is 0.866. Ready? Boom. Okay. Tangent of 30. Okay, well, that's going to be radical 3 over 3, whatever the decimal equivalent of radical 3 over 3 is. So tangent of 30 is, okay, let's just double check. Snap. Oh, get out of that before pressing division. There we go. Oh, so these will be decimal equivalents that I'll want to recognize, right? So 4 at the end. I always just kind of note the 0.577, but yeah, 0.5774. Now, we already know that sine of 45 and cosine of 45 are equal to each other, but what that should be equal to according to this is radical 2 over 2. So let's see what the decimal equivalent is to radical 2 over 2. Okay, 0.7071. Just double check cosine of 45, right? So you don't think I'm messing with your heads. See? And let's see if radical 2 over 2 gives me that. So radical 2, look at, I did it right that time, finally getting my head on straight. Why did I say anything? I mean, why? Why did I say anything? Because I knew I was going to mess it up there. This is where the graphing calculator will come in handy to help you check yourself when you need to be recognizing the right rational equivalent. Okay, so the right exact value of a trig versus the decimal approximation. It's the best way to put it. Tangent of 45, you're going to see is 1. We already did check that, right? It's 1 divided by 1, but it's going to be that here. So I just want to show you that that's going to happen. And then, of course, the tangent of 60, as we saw before, right, needs to be radical 3. So just to make sure that that matches up, there we are. And this is going to be, because the square root of 2 is greater than 1, right? The square root of 1 is 1. So the square root of 3 is also greater than 1, but less than 2. So here we are, 1.7321. Oh, I just did all those, right? So we know that this was the 0.7071. We know that this is 1.7321. And radical 2 really isn't super important in some of this stuff, but I'll just show it to you. It doesn't match with anything up there, but you should probably recognize 1.4142, okay, as the square root of 2 in a decimal approximation. You did all this stuff in geometry, but it really pays to practice it again. Do make sure you're practicing having your calculator in degree mode, checking for that, as well as just typing in. Just the general type in of these things is important to know how to do and to practice before you get into a situation where you have to do it. Okay? Also good to recognize the relationships, and so do make sure you know that. I believe the majority of what I ask you in your homework tonight is taking a triangle and just stating the ratio relationship in a triangle where you know all the sides, okay, and just compared to from this angle, tell me the ratios. I know I added some of these to just keep practicing, okay? Well, that's it, guys. This is where we're going to stop so that we can take a little quiz. And yeah, then we'll keep moving forward with finding missing sides and missing angles using these trig ratios to solve equations. Okay, set up and solve equations. So that'll be the next application of that. We'll look at trig versus Pythagorean theorem, and we'll look at solving word problems that require trigonometric use. All right, trigonometric ratios. Okay, guys, let me know if you need something. I'll talk to you soon.